Good evening. I'm Elisa Maggio. I would like to thank the organizers for giving me this opportunity. So, okay, I will talk about gravitational waves as probes of gravity in the strong field regime. And they allow us to understand the nature of compact objects in our universe. I will describe several alternatives to black holes, the so-called exotic compact objects. They might be unstable and they will emit a different gravitational wave signal. So on September 14, 2015, the first gravitational wave has been detected. And this was the coalescence of two black holes. The signal is characterized by three stages. So there is an in-spiral when the two bodies orbit around each other, and the emission of gravitational waves makes the orbit to shrink. Then we have the merger, and then we have the Ringdown, where the final remnant relaxates to stationary solutions. I'm not able to move. Okay. And I'm particularly interested in this final stage because I want to understand the nature of the compact remnant. I have some issues in moving the slide. Yeah, I don't know why. Okay, sorry. Okay. So do you see the screen now?
Now, yes.
Yeah, maybe I will do it like this. Okay. So practically the Ringdown stage is dominated by the characteristic frequencies of the remnant, and these are called the quasi-normal modes. And they are complex frequencies which describe the response of the compact object to the gravitational perturbation. Practically, the Ringdown phase is a superposition of exponentially damped sinusoids whose frequencies are related to the real part of the quasi-normal modes and whose damping times are proportional to the inverse of the imaginary part of the quasi-normal modes of the remnant. So practically, from a detection of the Ringdown stage, we can infer the quasi-normal modes of the remnant and understand its nature. Let me point out that if we have a negative imaginary part of the frequency, we have an exponentially damped sinusoid, so a stable remnant. Whereas if we have a positive imaginary part of the frequency, we have an unstable remnant. And we will go back to this feature later on. So, so far, the two LIGO interferometers in the US and the Virgo interferometer in Pisa detected 10 binary black hole mergers that are shown here. So the small dots are the masses merging into a final remnant. And however, only for the first gravitational wave event called GW150914, we have detected also one quasi-normal mode frequency. And this frequency is compatible with the one of a rotating black hole as described by general relativity. However, some alternatives to black holes are not excluded. And so we need to model them better and to have a larger sensitivity in future detections. So from a theoretical side, exotic compact objects have been conceived. They are some geometries which are characterized by the absence of any horizon. So they do not have neither the event horizon nor the curvature singularity. And they can be as compact as black holes, so they can mimic black holes in terms of the electromagnetic observations we did so far. However, they are able to solve some paradoxes associated to black holes from a semi-classical point of view. For example, black holes are thermodynamically unstable due to the emission of Hawking radiation, and they have a huge entropy which is far in excess the one of stellar progenitors. So there are plenty of models of exotic compact objects, which have been organized here depending on their compactness, but I'm mainly interested in the ones which are the most compact ones, characterized by Planckian corrections at the horizon scale of black holes. So the models that I analyzed are rotating exotic compact objects described by the Kerr metric, where they have a surface which is a bit outside the would-be event horizon of a black hole. And this bit is parameterized in terms of this epsilon, which is microscopical in the limit Planckian. So practically this solution doesn't have the event horizon singularity and is perfectly regular in the interior. And we parameterize the interior of this object through a surface reflectivity coefficient. And this is a complex value. We will analyze the case of a perfectly reflecting surface, which is the opposite of a black hole, which is instead perfectly absorbing. And then we will analyze also solutions which are partially absorbing due to viscosity or dissipation. So
with respect to what? To electromagnetic reflecting to respect to which field?
Every field, yes. So here I am, in this presentation, I'm focusing on gravitational field, but I've analyzed also scalar and electromagnetic fields.
What do you mean by reflecting from the point of view of gravitational field?
So I mean that it is practically a scattering problem. If you have an ingoing wave starting from infinity towards the compact object, when it reaches the surface of the object, it is totally reflected back.
Okay, so you are considering perturbation on the background of a given metric.
Exactly. Yes. Yes, because because I want to describe the gravitational perturbation, how it's modified in the case in which it is reflected and not totally absorbed. And I will show you in a few slides some plots.
Okay, thanks.
And these geometries, these rotating geometries, however, they might be unstable due to the so-called ergo region instability. In fact, the Kerr solution is characterized by the existence of an ergo region, which is a region between the infinite redshift surface and the event horizon of the Kerr black hole. In this region, negative energy states can exist. So in the black hole scenario, what happens is that if a particle falls into the ergo region, it can split in a negative energy particle plus a positive energy particle. And because of the presence of the horizon, the negative energy particle is forced to fall into the black hole, and the outgoing particle has an energy larger than the initial one. And this happens because you are extracting in this way energy from the black hole. And this is a well-known process called Penrose process, which allows to extract energy and angular momentum from black holes. Now, in the case of exotic compact objects, since we don't have an event horizon, negative energy states remain in the ergo region, and it is energetically favorable to cascade towards more negative energy states. This leads to a cascade process, which ends up in an instability of the object itself. And only by absorbing these negative energy states through some dissipation or viscosity, we can actually have a stable object. So now, in the case in which this object is stable, now we see how the quasi-normal modes change. So the quasi-normal modes are derived by studying the gravitational perturbation on top of the background of the compact object. And the perturbation is described by a second-order differential equation subjected to an effective potential. Here I'm showing the effective potential for the black hole case. And this as a function of a radial coordinate, which represents the distance from the event horizon, which is on the left of this plot. So the effective potential for the black hole has a peak at a value which represents the unstable orbit of a photon around the black hole itself, the so-called light ring. Whereas, and then everything that falls in can only be ingoing and will be absorbed by the black hole. Whereas in the case of an exotic compact object, the absence of the horizon implies the existence of a cavity between the light ring and the surface of the compact object. So there are some trapped modes into the cavity, which will lead to a completely different quasi-normal mode spectrum. But from the point of view of the ring-down signal in time domain, what we see is that the prompt ring-down is the same for black holes and exotic compact objects due to the excitation of the light ring. Whereas in the case of exotic compact objects, we have subsequent echoes due to trapped modes that leak out through the potential barrier for tunneling effects. So practically, the initial ring down that we observed so far only in one event is the same for these alternative objects, but then we expect to see extra signatures in the signal. So now I'm going to show you the quasi-normal modes that I have computed for this object. And here I'm analyzing a perfectly reflecting surface against gravitational perturbations. And here I'm showing the real part and the imaginary part of the quasi-normal modes as a function of the spin of the object, which goes from 0, so no spinning case, to 1, which is the extremal case. And what we see is that the real part of the frequency change sign above a critical value of the spin. But most importantly, also the imaginary part change sign for the same critical value of the spin, making the object from stable into unstable. So a highly spinning exotic compact object is unstable. And this is essentially the ergo region instability I was discussing before. Here I am focusing on a specific compactness of 10 to minus 10, but we can vary this parameter. And here I show the critical value of instability as a function of the compactness of the object. And what we see is that for Planckian corrections at the horizon scale, even slowly spinning exotic compact objects are unstable. And furthermore, the time scale of the instability is very short compared to astrophysical time scales. But what we observed in electromagnetic and gravitational observations are highly spinning black holes. So it seems that these objects are not astrophysically viable. Please.
Just a question. When you said that you were looking at gravitational perturbation, but there are at least two modes of gravitational perturbation. So do they behave the same way, or this is just one of the two?
You mean axial and polar?
Yes.
Yeah, so they are different. So in the plot above, I'm showing axial modes, only axial. And in the plot above, I'm showing axial and polar. And you see that there are some differences, but both of them, they tend to 0. The critical value of the spin tend to 0. So they have, I mean, similar features, but they do not coincide. Indeed, this is an interesting feature of this object, because in the black hole case, axial and polar modes are exactly the same because of some symmetries, whereas for exotic compact objects, these symmetries are broken and the modes are different.
Okay, thanks.
So, but there is a way to have a stable or rotating exotic compact object, which is by assuming a partially absorbing surface. And also, this is a more realistic scenario due to some form of dissipation or viscosity in the matter that forms the objects. And what I derived is that the absorption rate that you need in order to have a stable object must be at least as the amplification of factor of black holes. So practically what happens is that inside this cavity, between the light ring and the surface of the object, waves are amplified. And the absorption should be larger than this amplification in order to have a stable object. Going to the numbers, so in order to have a stable object with a spin of 0.7, let's say, you would require an absorption of 0.3%. And this can be achieved by just ordinary matter through dissipation. However, in order to have a highly spinning object, you would require very high percentage of absorption, and no known matter up to now is able to reach these values. And now I'm going to describe you, in the cases in which this remnant is stable, how is the gravitational wave signal emitted by these objects. So there has been a recent paper which writes the gravitational wave signal emitted at infinity by the exotic compact object as the signal emitted by a black hole at infinity plus the echoes due to the reprocessing of the signal emitted by a black hole near the horizon. And according to this description, practically you can write the gravitational wave signal with the black hole parameters plus the two parameters of the exotic objects which are contained in the transfer function. So the standard black hole Ringdown parameters are the mass and the spin of the object. Then we have the amplitudes and the phases of the plus and cross polarization and the starting time of the Ringdown. So we have a few parameters which would allow us to search for this feature. What I did was to derive an analytical template for this. Here in these plots, I'm showing the absolute value and the imaginary part of the analytical template, which are the thick lines, compared to the thin lines, which are the results of a numerical integration, and they agree pretty well with each other. The blue line is for the non-spinning case and the red line for the spinning case. And these characteristic peaks are due to the excitations of the quasi-normal modes of the exotic objects. And you wouldn't see them in the case of a black hole remnant because you don't have these characteristic trapped modes into the cavity. So here the template is as a function of frequency. Now I show you the template as function of time in the non-spinning and the spinning cases, and for several values of the reflectivity coefficient at the surface. So here we are considering the initial part is the black hole Ringdown, and we are starting with the Ringdown, which is purely plus polarized, represented in blue. And then what we see is that we also have a cross polarization in the echoes in the cases in which the remnant is spinning, either in the cases in which the reflectivity coefficient is complex. So it has also an imaginary part. And these two features have never been analyzed before. So far, there were templates which didn't consider the remnant spinning and didn't consider complex reflectivity coefficients. And what we show in these plots is that these features are relevant and modify the gravitational waveform in an important way. And I want to focus particularly on the relevance of the complex reflectivity coefficient, because in these three cases, I'm showing the same absolute value for the reflectivity coefficient, but with different phases. For example, what we see is that when the reflectivity coefficient is equal to 1, we have always the same wave in phase, which has every time lower amplitude and a different frequency content. Whereas when r is equal to -1, every time the wave is inverted in phase. And when we have a phase of pi/3, we see that, for example, the cross polarization is null every 3 echoes. And so these are additional features which should be considered in order to perform searches for these signals. So far, there have been research groups claiming of having observed echoes in LIGO Virgo data. And they used a very simple model in order to achieve this. However, there has been a debate, which is still ongoing, about the significance of these, about the evidence of these claims, and so this research has been followed by some negative searches. What is known is that we would require third-generation detectors or space-based detectors, which have a larger signal-to-noise ratio in order to actually say something about the remnant of mergers. And here I performed the Fisher analysis in order to see how much we can constrain the reflectivity coefficient of these objects with next generation detectors. So it is expected that in future we can detect or rule out these objects. So I go to the conclusions. Essentially, I've shown you that with gravitational waves, we can understand the nature of compact objects in our universe and look for new physics near the horizon. And I've described you some alternatives to black holes, and we have seen that rotating solutions are affected by an instability in case of perfect reflection, but they can be stable in case of partial absorption. And I have derived an analytical gravitational wave template for the Ringdown and the subsequent echos. And as a further development, we would like to do accurate match filter searches for these echos with these new templates. Thank you for your attention.
Thank you very much. And let's ask whether there are questions or comments to this talk.
Just a curiosity, but with the present detector, can you observe the two polarizations of a gravitational wave? How
Yes.
much can you detect?
Yes, we can observe very well the in-spiral phase. We have observed so far many of these in-spiral phases and merger. The Ringdown, as I said, is exponentially damped, so it's challenging to see the signal in this final region. But yeah, as I said, so far we observed 10 binary black holes, and then we observed 1 binary neutron star. And there is also the third observing run, which has just ended, and there will be many, many more detections. So we are still waiting for new data to see if they actually detected some parts of the Ringdown.
Can I ask a question?
Of course.
At the end of the day, I mean, if you have to go beyond the phenomenological description of this object, what are they?
Yeah, so yeah, what I showed is exactly a phenomenological description, but there are specific models, like there are, for example, boson stars, so objects characterized by bosons. There are, yeah, plenty of models. There are also like fermion stars, so different models of the interior. Practically, yeah, either there are objects which have some dark energy inside and are supported by some form of matter. Now here I didn't go into the detail of all the models, but they are well defined, and so you could also focus on some of these models.
I mean, one of the attractiveness of black hole is that there is some kind of universality, namely they behave universal no matter what. Now you are saying that also this is the case for this exotic compact object, namely they can be made by many things, bosons, fermions, whatever, they also behave universally as well?
No, they will have different compactness, and they will have a different reflectivity coefficient at the surface. So I'm parameterizing all these differences in 2 parameters. Yeah, I agree that black holes are universal, but they have singularities, which is something I don't feel very comfortable with, and also other researchers. So these models are all without any singularity. And the main point is that apart from the event horizon singularity, the black hole have a singularity in the center, which means that general relativity is breaking. And these models instead are regular everywhere.
Okay, thank you.